So just as a quick, this is actually the beginning of the second session, but just to update us. Oh, no, it's actually the wrong session. Hang on. So let's just do a little recap. So we have so far come across these first four. We're going to do fifth list now, which are probably the simplest. So we have the first vectors. These are like arrays in other languages. These are just ordered collections of a single data type. So you can't mix numeric and characters and expect to be able to do mathematical operations on the numeric parts. Importantly, they are ordered. So the first position is always the first position. That allows us to index these. The equivalent non-ordered would be things like sets in Python. We don't really have that concept so much in R. We then came across matrices, which are like vectors, but 2D. So we have rows and columns. But again, like vectors, these are ordered. So we will always, the first row will mean the first row. But they also have to be a single data type. So once they're numeric, if we add a character, they all become character. Okay, so that's very important for when we start to do operations on matrices later on. Matrices hold things like our, if we're doing RNA-seq, single cell, matrices hold the count data, the signal at a particular peak, gene versus sample. And the nice thing about matrices is they're a little bit faster to operate on than things like data frames. We then came across factors, which are like vectors. They're still ordered collections, but now they're categorical data. So they're handled a little differently. And importantly, we have this concept of levels, and we'll probably see that in a second. But these levels basically say the types of data values were allowed in that factor. A really useful object in R, which I think is copied across lots of languages, is this concept of a data frame. And this is a table, still ordered, it's 2D, except now we can have multiple data types across the columns. So we can have one column which is a factor, one which is a character, one which is a numeric. Okay. So data frames are really useful for ordering, collecting, or having different types of data in. Typically metadata and stuff is stored in data frames. And if we look, we can create our vectors just by using the combine function, right? And then we list the values we want separated by comma. In R, if you remember, always our arguments are separated by commas. If we want to create a matrix, we can then take our vector and just pass it to the matrix function. And we just need to say a few simple things like the number of columns we want, the number of rows we want. And if we want to control it, we can also tell it to fill by row or by column. So if we say by row equals true, it means the values will be filled in along the rows working down. If we leave it to the default, which is false, I believe, it will fill in along the columns from left to right with the values from this vector. Factors, again, we can pass a vector, but we'll typically say levels. And here we're going to say the levels in our factor. We're going to say R in Python. Okay, we don't necessarily need to set the levels. If we don't, it's going to set levels for us and it's going to put them in alphabetical order. What's important about, as we'll see in 2 sessions' time, is that this order also controls the order that things appear in our plots. So if I was to plot this later on, R would be the most left, and then Python would be to the right of it. And we can change this to control the order in the plots. When we start to do things like differentials and modeling, models, also the order is controlled by level. So it is important. Finally, we saw a data frame, and we saw that we could create data frames using this data frame argument, and we just provide it with a column name, here number, and I'm going to give it a vector of numbers. I can give it a factor, and I'm going to give it the factor from here. And this will then contain different data types. So just to remind us, we can do indexing using the square brackets. So we use parentheses and round brackets to create functions. So here we used it in C. But if I want to get the 10th value out, I use square brackets and I put 10 and it gives me the 10th value. If I want to assign a value to the 10th one, I can just do the same thing, but now I'm going to assign using our assign value, and I'll put 0, and then my 10th value is replaced with 0. Similarly with matrices, here I'm just going to create a matrix like we just discussed. I'm using matrix, 2 columns, 5 rows, 2 columns, 5 rows. And I'm going to say by row equals, can't quite see, but it looks like it must be true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then if I want to pull out the first row, I can now index using a comma. And that's because matrices have 2 dimensions. So I need to provide a row index or a column index or both. So if I want to get the row, I go before the column, sorry, comma. So it's typically rows, columns in R. So rows come first, and I can pull out the first 2 values as a vector. Similarly, if I want to pull out the column, I can just say comma 1, and it will give me the first column. I can also do all the replacement I want as well. So I could replace here, first row, first column with 0. There it goes. Or I can replace the entire second column with 100, and here I've replaced the entire second column. Okay, importantly, I'm going to emphasize this again. In this case, I'm going to replace the second column, first row with a character string. The whole matrix is changed to a string. Okay. So previously, I could do arithmetic operations on this. As soon as I've changed any value in that matrix to a character, the whole matrix is polluted. It's become a character matrix. That's kind of signified by having these quotes around it. Similarly, we can create data frames like we just saw. Importantly, they can hold different data types. Oh, sorry, we can also use logicals, sorry. So here I have a vector. If I want to evaluate which ones of these vectors are above 9, create a vector. We can do a greater than 9, and it will turn my vector into a logical. So it returns a logical vector the same length, but now it will say false when it's not true, which will be for the first 9 values. And the last value it's going to return true because that value is above 9. So as we saw, and we'll see again today, we can use these for then index. And if I want to pull out values which are greater than 9, I can use this, and only the true will pull back into that. Last thing I think is, I think this is the last thing on data frames, maybe. Oh, 2 more. So we can also use something special with data frames. We don't need to do this indexing with square brackets necessarily. We can also just name the column we want to pull out. So here I have a column, 2 columns, number and factor. I can do $factor equals R, and it's going to pull out this column and then evaluate which ones equals to R. True, false, true, true, false, right? So that works. I think we can remember we don't necessarily need to write the full factor here. It's some type of autocomplete. So if I wrote fac, as long as it's unique enough to recognize it's only that column, we'll be able to return the values from the columns for me. Like I just saw, we can, like I just said, we can create these logicals from our vectors. They're now here greater than 5. So the first 5 values are false, the next 5 are true. We can then use that to actually index our vector. So in this case, only the values which are true, so it'll be the last 5, will be replaced by 10. I'm going to say a vector, and then I'm just going to say the values greater than 5 assign 10. And now if I look at my vector, the first 5 are all the same, and anything above 5 is now 10. Just to keep us on our toes, for data frames and factors, we can't replace value in a factor with something which isn't in the levels of that factor. So in this case, creating a factor of R, Python, R, Python, I set the levels to be R or Python. If I then try and add a value into this called not Python, it gives me a sensible warning, and it's going to say invalid factor level NA generated. And then I can see for every value which was here R, which I've tried to replace with not Python, it's actually just giving me an NA. It's a simple solution to that, and that's to, in some way, update that factor to include that level. And in this case, when I create it, I'm going to be a little bit more forward thinking, and I'm going to provide an additional level, R Python. I'm going to put not Python. And even though it's not in the original factor, we now have a level for it. And now I can replace those values and not get anything on. So factors, if you're going to replace anything in a factor, you have to make it aware of that level. Okay, so that's it. And we're going to go back to our main class. Feel free to stop me if you have questions as we go. We haven't come to lists yet, actually, have we? So I'm going to do lists now. Yes, sorry. Once my computer wakes up a bit. Have a look. Okay, so I am going to come back and run through these exercises at some point. So I'm going to do this probably at the end of a class, but I'll also record it. So you don't need to hang around. It'll come up on YouTube as well. So lists are the final data type we're going to look at. And I would say our lists really provide this general container which can hold any types of data. And it can hold data of unequal lengths as well. Okay, so lists are a very simple kind of object in some way where you can store different types of data, but in the same kind of structure. So we're going to do that by first creating our first element of our list. We're going to create a vector 1 to 4. I'm then going to create a second element. And I'm going to create a matrix 1 to 10, 2 rows, 5 columns, and it's going to be by column. I'm not changing any of the defaults. And then I'm going to create a third element for my list, which will be a data frame. And that's going to be 1, 2, 4, 5 in column 1, and then the actual some string in the second column. Maybe I've got something. If I then want to turn or create a list, very simply use the function list. So here's going to be a list, open my brackets, and then I just provide the elements I want to put in my list here. So I'm going to put my first element, my vector here, my second element here, and my third element. Okay. Now I have a list, and if we look at this, it already looks a little different. We have what is our first element here. So that's our vector. We have our second element here, which is our matrix. And then we have our data frame here. And that's our third element. But we can already see, whereas these look like conventional matrix, I have my rows here, my columns, I have my indexes. This looks like a standard data frame, standard vector. We have this kind of strange double square brackets and a 1 in it, double square brackets for 2 in it, and double square brackets for 3. So lists are a little bit different. I mean, the first thing, lists and vectors, lists can hold different data types. Still ordered, but they can hold different data types differently. Just as with vectors, we can also provide names for this. So in this case, I may want to replace those 1, 2, 3, and I'm going to give them names up front. So I can do that by doing list. And just like with data frames, where I will provide the name of the column, if I want to create it this way, here I can do first element, second element, third element. And now I have a named list where we have the actual names kind of above the element here. So lists, just like with other data types, can be indexed, but they have slightly different ways of indexing for very particular reasons. So using a square bracket, our standard way of indexing on a list will pull back just the element you're looking at or the elements you want to pull back, but it will keep them as a list. Okay. So I think I show that maybe now. Here we go. So in this case, if I do my list and I just try and get the first one out, it's still a list. It's a list of length 1, But you can see here, it's still a list. And inside that first element, I have my vector. Okay, so there might be reasons that you want to pull out 4 or 5 elements and keep them as a list. Okay. If I actually, and a lot of the time you do, you want to get access to the value within that, I have to use my double square brackets. Okay, so rather than here, I'm pulling out a list which contain my vector. If I want to just get into and get that vector, I'll do double square brackets 1, and now I get my vector back. Okay. Hopefully that makes sense why you'd want to do that. Often you want to subset a list just to certain elements, but we want to, it has to stay in the list structure. Otherwise, how would these elements exist next to each other? Okay. When we want to go extract a value, such as the vector, to then go operate on it later, we want to actually get the vector itself. So we'll do the double square brackets. You can also, like with data frames, do this $. And here I'm going to do $. First. And that's going to extract the element itself, so the vector itself. Again, like with data frames, we have autocomplete. Lists can also be joined, but there's a slight difference. I'm not going to sure if I'm going to show this. Yes, between joining vectors and joining lists together. So here I'm going to create our list again, my name list, and then I'm going to create another list which has one element, 4th, which is a vector of 4 and 4. If I combine these two lists together, and here I'm just going to show the first and the 4th element in single square brackets, right? It's going to return a list back to me. And we can see that the 4th here, it's actually just concatenated on this list. So we have a 4th element called 4th containing that vector. A common thing I think I see people do is they try and combine lists like this. So we have a list here, my list from before. And then they're going to try and combine it with a vector. And they expect that that's going to be added as its own list element. Okay, it's actually not. What it's going to do is create 2 elements for you. The first one containing the first value here, 4. And then the second one containing the second value, 4. Okay, so if you want to create or add a new element, you need to create another list first before you combine it to your previous list. Otherwise, you end up in this kind of situation where you're adding multiple list elements. Lists also have their kind of opposing function called unlist. And I think this will become useful as we start to do some kind of compiling data together. So we have this concept of kind of flattening out a list. So if the list is compatible, so if we have things which could possibly be combined together, so in this case, I'm going to create a list, and all elements will be vectors. Right? 1 to 3, 2, 6, 7, 1, 4, 7. We look at that, it's like a normal list. It's separated out with our different vectors. In this case, if I apply the unlist to this, it's then going to do something kind of smart. It's going to give me a long vector, and it's going to take the names of the list, and it's going to attach them to here so that we get like a named vector. And you can see it's done first 1, first 2, first 3, corresponding to the first, second, and third position in this first one. 1, 2, 3, and then second 1, 2, 3 is coming from here, and then third and off the screen. So a common thing to do actually with these type of data, and we're going to show you some shorthand for this as well, is to try and unlist a set of results and put them straight into a matrix. Okay, so here we have a list of vectors, all the same length. And this could be the result of another function giving you back a list of these result or these kind of vectors. If we want to turn that into a matrix, we can just unlist it. And then we'll get a nice long vector like here. Right, those are then suitable to go into our matrix function. And all I need to do is give it, for n rows, I'm going to say number of rows the same length as my list, 3. Number of columns is 3, because I know we have 3 elements in each. I'm going to say work by rows. And finally, we have one last thing we can give it, which is dim names. And I'm going to give it the names of my list. And now we can turn this list into a matrix, which we may want to then start to do some operations on. I show this example because this is something we're going to do in a little bit. The results will come back as a list, but we don't want to operate it as a list. We want to turn it into a matrix. Then we can do our kind of mathematics on that a lot easier. So lists are actually very straightforward, but ubiquitous. I'll move this a little bit. Sometimes, hopefully you know what objects you've created. But sometimes, when you're getting scripts of other people or functions returning objects to you, you're not entirely sure what they are. So we can actually use this class function to tell us what our object is. Most commonly, you may not know the difference between a data frame and a matrix. Right? They look reasonably similar. So in this case, we can just do class on our named matrix from earlier. It's going to tell us it's a matrix. It also tells us it's an array, but we can just worry about that first one. If I do class on my data frame, it's going to tell me it's a data frame. Yeah. We can convert from one class to another. Okay. So we may want to turn lists into a vector or something like this. So here I have my named matrix. It's two-dimensional. If I want to, I can turn that into either a vector or a character. Also, there is also as.numeric. So here I'll do as.character. And it's going to kind of flatten out my matrix for me, working here along the columns, the same as the default for when we create a matrix. We're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I turn this into a character, similarly, I can turn it into a vector with as.vector. Most usefully, what you're probably most likely going to try and do is turn a matrix into a data frame or a data frame into a matrix. Right? Because there are just some functions, some objects, it needs to be a matrix. If it's not, it's going to reject it and not allow you to. So a lot of functions internally will start with this kind of checking the class of the object you pass to it in some way. So if we want to, it's very easy. We can turn our matrix into a data frame with as.dataframe. If we want to turn our matrix into a list, we can do it as.list. So somewhere in there, there's usually a converter for you. And as we start to get to more complex objects, like genomic ranges, we can turn them back to data frames, because data frames are easier then to write out or print. Okay, so I think the final part on this session 1 is to look at how we actually really get data. So as it says here, most of the time you're not going to actually be generating data in R. You're going to be reading it in from external sources, a sequencing machine, a proteomics machine, some imaging. Usually it's as a table of some sort or as a file with multiple rows you need to parse in. But we're not going to be generating them R. We're going to try and be importing them from standard formats or external files. A standard format for data is a table. A lot of time it's summarized in something like this, where you have the first column being gene names, or I guess it could be something like this. And then you'll have the remaining columns with your numeric signal data, and you'll have your sample names across the top. Most data looks like that in some way. So R has lots of functionality to get data into our kind of matrix format or data frames. And the basic forms of doing this, or one of the most basic ones, is read.table. Okay, there are more particular versions of this, like read.csv, which will read in CSV files, but they can all do the same thing if you change some of the parameters. So here we can see read.table. The first argument it takes is the path to our table. So if you're in our working directory, there's a folder called data. And in there, there's a file called readthistable.csv, which is a clever name. So we need to give it the full path from where we are. So data/ actually gives it the path to go into that folder and read this particular table. We then want to also provide it with two additional arguments here. So I think if you do read.table, read.table, it will tell you the defaults. We could probably do that in a slide or now. But here I'm going to set our separator to be comma. And that means the separator between values, columns in your data. So quite commonly, data is comma separated. That means every value for within a row across the columns is separated by commas. And we're also going to tell it here, header equals true, which means treat the first row as our kind of column names. Okay. So if I do that on this file, which is a nice regular file for us, we can see that we're going to get our kind of table. This will be a data frame. First column is gene name. Second column is sample. Third column is sample again. If you want to read in from tab separated files, which are a really common thing, to get a tab, to specify the tab here, we don't put a tab in literally. We do this kind of shorthand \T, and then that will tell it to read tab separated files. We've got lots of this in our exercises. Okay. So read table does offer significant control over these arguments. Maybe my computer's a little slow, so I'm not going to hop back and forth. You can do that at the end. But one really useful argument is this row names argument. So this actually specifies which column, as it's read in, should it use as row names. Okay, so here I'm going to say from our previous session or previous slide, this I should probably treat as row names. So I'm going to say row names equals 1. Everything else keep the same. And I get my data frame back. But now I've got names, row names, rather than a column containing the row names. Okay. Can anyone tell me why that might be useful? Yeah, exactly. That's one really fantastic. You know, already I can use that as an index, right? Another really useful thing is, and as I said earlier on, matrices can only be one data type, right? So this is a data frame, but I could do as.matrix and turn it into a matrix. If I had left it like this, when I do as.matrix, this is character, the whole table will become character. If when I read it in, automatically put these into row names, I can straight away turn this into a matrix. It's all numeric, and it will go into a lovely numeric matrix and I can start operating on. Okay. It's going to save you 2 or 3 lines of code just to do it this way. Yes, I've got to take out this part, which is my bitterness about previous R version. So it used to be that when you read in tables, there is this additional argument. They just changed this argument here. That strings as factors is false. Okay. If you set that to be true, all your characters, when you read them in, will be factors. Okay. So row names here, these here would have been factors. That's a pain, and I think the default changed because it's very hard to replace factors. I have to reset the level. So most of the time, you don't need to do that. So I'm not sure why it was ever default, but they changed it. So right. There are a couple of other useful functions here, and I'm not sure we have any examples of their use, but I do have extensive examples of this in the exercises. And these are going to be really useful later on. So one is skip. And you can say, well, I know every time I get this file off a machine, I know every time this file is passed to me, the first 10 lines are information which is useful. Perhaps they've written notes for you, but you don't want to read them in. Maybe they're not fitted into a comma separated in any way, right? So we can say skip. I just want to skip the first 10 lines and it will skip them and start reading from that point. That's really useful. Another part which is very useful is comment chart. So there is some type of standard that the hash on your computer, so the hash key, which is Shift 3 for me, The hash is a comment. So we don't read that. It doesn't get parsed into the into our table. Okay. So by setting comment char to be hash, it will ignore any line which starts with a hash. Okay, so when we do things like peek calling, so max2, which is still used in single cell attack generally is one of the best peek callers. It puts all the information on how it called the peek, all your kind of parameters you've set are at the top of the output file, and they're after a hash. Okay, we want them in the file in case I want to know how did I call that peek, but we don't want to read them in because they're going to ruin our table. Just setting comment char equals hash, it will ignore those lines and you'll get your table. Okay. We have some examples in the exercises, like some pretty tricky examples of working with that. So the data table function can also read from HTTP, as long as that HTTP, HTTPS, FTP, as long as it is not private. So we have some on our GitHub IO page somewhere. We have the same table. I don't need to change anything. Read table will recognize it's a URL. It will automatically download it and read it for me. I just need to say sep equals comma, header equals true, and I get the same table. I think there is a version on Mac. I don't know what it is. But if you copy stuff to your clipboard, so if you just select the data in Excel, which you want to read into R, you can just select it. And in Windows, it's read table file equals clipboard, and it will then read that in, and you can start working that on. That might be useful. You might have something you want to pause in. There are a lot of packages kind of extending reading for things like this. Okay. So actually, I was trying to fix this example. It's a little bit. We're not going to do this ever in our class, but the really low-level version of reading data in R is scan. So scan can actually save you a lot of memory when you have huge files, because you can actually tell it not to read in certain columns. You can just read parts of it. So in this case, we're going to try and read this table again. I'm going to give it the same separator. The big difference is I can tell it what the columns will be. Okay, and I've done something stupid here, and I've actually left in a character in one of these columns, which is why they've come out as character. But in this case, I had 6 columns. I told it the first was the character. I did repeat, so I have 7 columns, and I have I put a character in here, so they've all come out as character. I'm sorry, I'll fix the example. Scan, we don't really use, but later on when we get to things like RSAMTools, reading in BAM files, we're going to use scan BAM. And that will allow us to read elements of these 100 gig files, but not read every bit of information in that file, just what we need. Okay, most importantly, we probably want to write our data out. So we've done our analysis, we have our hits, and we want to write that out to a standard file. We can just use write.table. Okay, so we'll do table, the one we just looked at, and then I'm going to say the file I want to write. I'm going to write it to here. Importantly, I'm going to say separator equals comma, so it's going to write out a comma separated file for me. You can open those in Excel, I believe. Just so I could put a tab there, and it could be a TSV. We know. There we go. If I look at my data, which I'm writing out, say here, I don't have any row names, right? Here I've got them still in this first column. And I think this is something which stings people quite a lot. If I say row names equals false, that's great. It's not going to put any row names in my file. And I'll say col names equals true, it will maintain my headers, right? So if we look here, I have some headers. I want these written out as well. So by saying col names equals true, I'm going to maintain them. They'll be in my file. That's important. The row names is a little bit of a pain. And we have a good example of this. And maybe once we get to the end, I'm a little worried my computer's slowing down with Zoom in the background. But if I said row names equals true, it's going to write out to the file. Basically, it will write out 1, 2, 3, 4, 5, 6, 7 out in its own column. The problem is that column doesn't have a header. Okay. So that means that your headers actually ended up shifted over by 1. Okay. None of your col headers now match up. This can be a real pain. You're going to see it in the exercises, and it means when you open it up, everything's off by 1 with your titles, and then you try and read it in again, and everything's off by 1. So one way to deal with this is just not to write out row names. And if you have row names, to move them into a column of its own and then to write them. If we want to actually just review our data in R, we can use these. You can actually just use the RStudio as well. But you can write head on our table. It will give you the first, by default, 6 lines. That has arguments. You can provide an n argument and see how many lines you want to see. And we could do tail just to see the end of our file. And if we want to set the number of actual rows we want to see, we can do head, table. And here I just want to see 3 rows. So this is useful when you have a massive file and you just want to see what the beginning and the end of it looks like, to get a sense of the actual full structure of the data. Because as you know, if you type that in and you just press enter, it will try and print a lot of the table, and it usually ends up looking pretty ugly in your R session. So in our first year I did this, maybe the second year, people wanted to know how to read and write stuff into Excel. So we added this session. So please, if you have questions or other things you want us to add, the formats you want to deal with, please let me know. So here we're going to use this Rio package. I think it's RIO package. Rio sounds more fun. And this actually is a really nice package because they basically wrapped up a lot of the work from other people. So there are packages to read in MATLAB data. I know someone said they were working with MATLAB at the first session. They've come back and take it off. SES, SBS, Minitab, I think we covered that when I was doing my videos. Excel, OpenOffice, XML, all these formats you may want to read, right? There is a package someone's written to kind of parse this, but we don't necessarily want to install 12, 15 different packages to deal with them. So we can actually just install this RIO package, and it's going to install all these other packages for us and give us a really nice way of interacting. So the RIO package, it can be installed using CRAN. I'm not going to reinstall it, but I'll show you this here. So if we want to install packages, I think we come back to this at the end. Oops. See if my computer can handle changing and recording at the same time. Maybe not. Oof. You know what? Maybe not. I'll come back to that. Okay. It's the expectation of changing screen while recording is too much from the computer. Okay, so you know, as I'll show at the end, I'll stop recording and I can show you. But if we want to install packages directly from CRAN, we can just do install.packages. I mean, this is like a normal function. Give it the name of the package, RIO. It will then do all the hard work for us. It's going to go grab that package, all its dependencies, and install them on our computer. So once this is installed, in order to get access to the functions within that package, we just need to run library and then in quotes the name of the package. Once we've done that, it's going to go get all these functions loaded. It'll give you some verbose warning about what it's done. And now we can start to use its special libraries of file parsers. Okay. So it has really just 2 or 3 different functions. But what it does is kind of nice, is it will scan this part of your file to see how to import it. Okay, so if I want to read in just a standard CSV again, I can just use this import function. I give it the path to my CSV, and it will read it as a CSV. It looks at the extension, and it will know it's comma separated, guess, and it will read it in for me. more usefully, perhaps, is that I can also start to take advantage of things like Excel. And I think Excel, OpenOffice are probably two of the major formats people want to read in and actually write to most of the time. So here, and this will be in our data file somewhere, but we have an XLS. And if I want to read the second sheet from this XLS, I can go import, I give it the path to my Excel file, and I tell it which. I'm going to say the second sheet. There are tabs, I need to get multiple sheets in an Excel file. If I wanted to, I could also actually just tell it the name of that tab if I've named it in Excel. And here I'm going to do metadata. And now I get the table. And this contains my information. Okay. So it's just as easy to read from an Excel file now as it is from a comma separated or a tab separated file. I might want to grab all the data in my Excel at one go. Right? So if I've got multiple tabs in my Excel, I can use this different function, which is import_list. And that gives me back, I imagine, a list. And each element of that list will correspond to a sheet in my Excel. So we have the second sheet with metadata. The first sheet was expression scores. You can see I'm bring out the names from here. But that's one way that I can get all this data from an Excel into a list of here tables. It's going to be data frames. I've got the expression scores and I've got the metadata. If I look, because it's a list of data frames, I can just use my dollar accessor. I can also do my double square bracket. Put my name and my element there. But we have our expression scores, which we've been looking at. But now I also have the metadata as well. So I might want to do my mathematics on here. But this is going to tell me the group information to actually compare. So it's really useful to have data. And Excel, these multiple sheets, really does match up with lists, that concept we have in R already. So here we might want to also export data. Okay, so here I can export a single tab if I want. So I'm just going to take the expression scores element from the list, and I'm going to export that into an XLSX. I think that's the latest version of Excel. Okay, so that's going to export that. Just need to say file, where to export it. If I want to export multiple tabs, multiple spreadsheets, right, into one Excel file, I can actually export a list using this as long as it's a list of data frames. I'm going to just rename them. I'm going to call one express, expr, one meta. And the same way I can do export, give it a table, give it the path to the Excel SX I want to create. And we'll do that for okay. So I think that's a really nice thing about, I think that's the end of our sessions here. The really nice thing about the RIO package is it, by just having these really two, maybe three functions, import, export, import list, it allows us to handle a lot of different data types. I don't do much SAS, so I haven't got many examples. I hear a lot of people do. Happy to add an example of people here. But if you do question mark import, once you've installed it, you'll see that it has lots and lots of options. Cool. How are we doing for time? Oh, they've taken the clock from me. Have I just been recording my face for the last hour? That's going to suck for the video. Oh, well. Okay, well, we'll move on to the second session. Let's share that. If I have, I'll re-record it. Okay. What time did we start? So roughly 1, right? Let's have a little break before we hop into the second one. So let's just take 10 minutes.